Alrighty, this is the standard model. Now, the standard model is very different to what you guys have seen so far this year because it's dealing with very, very much subatomic particles and quantum mechanics. And quantum mechanics is just flat out weird sometimes, alright? So in the standard model, we have three different types of particles. We have quarks, we have gauge bosons, and if I scroll down, we also have leptons. Now, years ago, it was theorized by a whole bunch of people that everything was made up of protons and neutrons. So, you look at, here's a proton, here's a neutron, here's an electron. We can build anything we want out of that sort of stuff. And we're talking not like thousands of years ago, we're talking about the 1930s. So it's really not that long ago. Then in 1964, these two dudes, I don't know really which one's which, but anyway, they started talking about how things were made up of more than just protons and neutrons. So there was models of things or particles that they're actually seeing that were just completely different. They weren't made up of protons and neutrons at all. And they were seeing all these different weird things and wondering how on earth they actually could exist. Now, long story short, if you zoom in on an electron, that's it. An electron's an electron. You can't cut it into smaller bits. An electron is its own fundamental particle. But protons and neutrons aren't. They're made up of other stuff. And this other stuff that these two guys, Gell-Mann and George Zweig, Murray Gell-Mann and George Zweig, came up with these tiny little particles called quarks or quarks, depending on which YouTube video you're listening to. And they kind of hypothesized that these new particles that they were looking for or trying to, explain, I guess, could actually be the basis for protons and neutrons themselves. And when you smash a couple of protons together, you get a whole bunch of other weird stuff come out. And this could also help explain that. So they came up with the basis of the standard model, I guess. So in the standard model, we have 6 quarks. We have an up quark and we have a down quark. Now, the up and the down are the most common ones. These are the, I guess, most stable to an extent. And because they're the most stable, they're the ones that make up the protons and neutrons. So if you want a proton, you want something that's positively charged. Now, an up quark has plus 2/3 of a charge. A down quark has minus 1/3 of a charge. So if you have two ups and a down, you get two lots of 2/3, take one lot of 1/3, you end up with plus 1 as a charge. So 2 ups, 1 down make a proton. If we have 2 downs and 1 up, we have 2 lots of minus 1/3, 1 lot of plus 2/3, and we end up with 0 charge overall, which is why a neutron is actually 2 downs and an up. So the only difference between a proton and a neutron, other than a tiny little smidgen of mass, is actually the up and the down quark in there. So there's 3 quarks in these things, in a proton and a neutron, and one of these quarks changes from up to a down. Now it's not a proton anymore, it's a neutron, which is a little bit weird. There's other quarks, the charm and strange in the top and bottom. Charm and top have plus 2/3 of charge. Strange and bottom have minus 1/3 of charge. Now, the top and the bottom and the charm and the strange are huge in comparison. So if we look at if we turn the amount of mass in an up quark into joules of pure energy, so E equals mc squared, if we manage to do that, what we're looking at is a bit over a meg electron volt. In terms of these two, especially, we're looking at gig electron volts, and that energy comes from collisions at the LHC. So if we make protons run incredibly fast towards each other, so we're talking pretty much the speed of light, their masses become their energies become and their momentums become, they approach infinity as these particles approach the speed of light based on their Lorentz factor being so bloody huge. So the extra energy, I guess, comes from those sorts of things. Now, in the standard model, we also have, or in particle physics, quantum mechanics, we also have other types of of particles. So a baryon is something that's made up of 3 quarks. So a proton, which is 2 ups and a down, and a neutron, which is 2 downs and an up, is made up of 3 quarks. Now, don't know what that's doing. These 3 quarks are consistent with every single baryon. So you might have a baryon made up of an up, a charm, and a strange quark, for instance, or it might be a top and 2 strange quarks. I don't know what that particle would be, but every single baryon that's made up of 3 quarks, every single particle that's made up of 3 quarks is considered to be a baryon. Mesons are another thing that you might hear, or you will hear. Mesons are made up of a quark and an anti-quark pair. So it might be a top quark and an anti-strange quark. All right. So if a strange quark has a charge of a third, the antiparticle of a strange quark would be an anti-strange, and it would have a charge of minus a third. So it would have a charge of plus a third. So if you got a particle that was a down and an anti-strange, it wouldn't have a charge at all because it would be plus a third, minus a third, take plus a third, so it would cancel that to be nothing. So you'd end up with a neutrally charged particle. Now, the next set of particles that we're going to talk about here are the gauge bosons. So gauge bosons are force carriers. So there's a force or a particle exchange between things with the electromagnetic force. So the electromagnetic radiation, the electromagnetic force, which is between charges and magnetic fields and whatever. The force carrier is the photon. So when an electron is orbiting a hydrogen atom, for instance, there's actually a photon that's the exchange particle that's actually carrying that force. It's too small for us to see and probably too small for us to detect, but it's there. The weak nuclear force is carried by the W plus and W minus and Z bosons. These are generally responsible for radioactive decay. The gravity force is responsible. So the graviton is responsible for the gravity force. Once again, physicists with their naming conventions, really great and creative and stuff. This one here is so small. So the graviton. Hang on, let's see if I can find a highlighter. The graviton is so small that we haven't actually been able to detect it yet. So we found all of the others, spotted all the others, and all of this stuff, and the leptons that are down further. The Higgs boson, we found that one, but the graviton, so small, so insignificantly weak that we actually haven't found it yet. The last one is the gluon. It's literally called the gluon because it glues nuclei together. A nucleus together. So it's the thing that binds protons with protons and protons with neutrons and neutrons with neutrons, but also it binds up quarks to other up quarks to hold the proton together. All right. Again, that's probably one of the stupidest naming conventions I've ever heard in terms of particle physics or in terms of physics whatsoever. But, there you go. The other particles that we're going to talk about are leptons. Leptons sound weird. A lepton has a lepton number of 1. Anything that's not in this grid of 6 here either has a lepton number of -1 or it doesn't have a lepton number at all. So we have the electron and the electron neutrino. You may have seen this, you would have seen this. You would have seen this and you may remember it from last year when we had a neutron in a nucleus decaying into a proton, and the beta minus particle, which you hopefully remember is actually an electron, plus the antineutrino. And we also had a proton in a nucleus decaying into the positron, plus the standard neutrino. All right, so what we're going to do now is quickly balance some lepton numbers for funsies. So an electron, a muon, and a tau particle, they all have a charge of -1, and they all have a lepton number of 1. The electron neutrino. So there's a neutrino associated with the release of an electron. There's a neutrino associated with the release of a muon. There's a neutrino associated with the release of a tau particle. And these all have a lepton number of 1, but they don't have a charge at all. If we have an anti-electron, you guys would have seen that as a positron last year, that has a lepton number of -1 and a charge of +1. That's the anti of that. If we have an anti-tau, same deal, has a charge of +1 because it's the antiparticle, and a lepton number of minus 1. So if we go through here and we balance these things, we're looking for 3 different things. We're looking to balance mass, we're looking to balance charge, and we're looking to balance the series of lepton numbers. All right, so first of all, mass. Let's go orangish. Mass is the numbers across the top. So we're looking for 1 equals 1 plus 0 plus 0. Sweet. Mass, all good. Now we're looking for charge. 0 equals 1, take 1 plus 0. Sweet, we're all good. Now we're going to balance lepton numbers. A neutron is not in this table here at all. So a neutron has a lepton number of 0. A proton, also not in this table, lepton number of 0. An electron, let me do this. An electron, charge of -1. An electron is, in this table here, is as a lepton number of +1. The anti-neutrino, so this is the anti-electron neutrino. The electron neutrino has a lepton number of 1, so its antiparticle must have a lepton number of -1. 0 equals 1. 0 equals 0 plus 1, take 1. Sweet, that all works out. Similarly down here, we've got a charge of 1 equals 0 plus 1 plus 0, good. Mass of 1 plus 1 equals, plus 1 equals 1 plus 0 plus 0. And we also have the lepton numbers, 0, 0, minus 1, because it's the antiparticle of the electron, and plus 1, because it's the standard electron neutrino. So when we go through and we balance these equations, what we're looking to do is follow 3 rules. So we're looking to balance mass, we're looking to balance charge, and we're looking to balance lepton numbers. So we are also going to look at the individual lepton numbers, the electron lepton number, the muon, and the tau lepton numbers. Because you can actually have situations, especially in questions in test exams, where it might be that another particle exists over here, and we're trying to make sure that the nuclear reaction can in fact happen. So, long story short, there's some weird stuff that ends up happening. Oops, sorry, I'm sitting on the floor. We have an up, a down, a charm, a strange, a top, and a bottom quark. You can see 4.18 gig electron volts, 4.8 meg electron volts. We're looking at somewhere around, 1,000 times difference between these, the down and the bottom, and 2.3 meg, 173 gig. So obviously, there's a lot of energy in this system. The electron, muon, tau, electron neutrino, muon neutrino, tau neutrino are all leptons. They have a lepton number of 1. Ignore the halves and stuff, their spins. Then we have the gluon, photon, Z boson, W boson, and the graviton, which isn't in this because it hasn't been detected yet. All right. And we have some of these, the bosons are all, let's keep scrolling. The bosons, as I'm talking, the bosons are all to do with force carriers. So we have the photon for the EM force, the Z and W bosons for the weak force, the gluon for the strong force, and the graviton, which isn't on there yet, for the strong nuclear force. And there's a whole bunch of other sorts of things in this document. Now, a lot of this stuff came from those guys that I was talking about earlier in the video, from diagrams like this. So if you smash protons together there and they split up into tiny little bits that are fractionally charged with different lots of masses, this is going to be in the LHC, magnetic field, and all these spirally things through bubble chambers and whatnot are related to charges that, particles that aren't charged because they go dead straight through. Particles that are positively charged because, let's say, they go up like this, or negatively charged because they go down like this. And the radius of curvature is to do with the magnetic field, and how much of an influence, so BI or QVB sine theta, and how big that force is to cause mv squared on r, so uniform circular motion. So looking at all these sorts of things and seeing all the random swells, seemingly random swells, these guys are able to detect whether a particle is a new one, whether a particle should exist or shouldn't exist, but also this guy here that's come up this way and disappears. by here. That's because it's actually decayed. So if I go back to that thing up here, where are we? These guys, the up and the down, they're nice and kind of stable. The top and the bottom, the charm and the strange, these things live for almost 0 time at all. So we're talking 10 to the minus 15 to 10 to the minus 24 seconds. They have an incredibly short lifespan. So they almost immediately decay into the series down. So the top into the charm, into the up, the bottom into the strange, into the down. All right. So yeah, the standard model is a bit weird, but we basically just need to follow those few rules over here where we're balancing those things: the mass, the charge, and the associated lepton numbers. Everything else would be given to you, or you'll have the information to be able to solve the problems yourself.